NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve quadratic equations step by step using the quadratic formula. We'll introduce the discriminate, explain the three cases, and finish with a fully worked example. First, let's place an example label. Then, we show the general quadratic equation, ax squared plus bx plus c equals 0. Step 1. State the quadratic formula. The solutions are x equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. Step 2. Define the discriminate. We let capital delta be equal to b squared minus 4ac. Step 3. Rewrite the formula using delta. Now we have x equals negative b plus or minus the square root of delta over 2a. Step 4. Consider the three possible cases for delta. If delta is greater than 0, there are two distinct real roots. If delta equals 0, there is one repeated real root. If delta is less than 0, there are two complex conjugate roots. In this lesson, we solve a quadratic by strictly following the delta equals 0 case of the quadratic formula algorithm. Our example is 2x squared plus 4x plus 2 equals 0. First, write the general quadratic and its discriminate. Ax squared plus bx plus c equals 0. The discriminate delta equals b squared minus 4ac. Case 2. If delta equals 0, then both formula branches collapse to the same value. For x sub 1, we have negative b plus the square root of delta all over 2, which becomes negative b plus the square root of 0 all over 2, which equals negative b over 2a. For x sub 2, negative b minus the square root of delta over 2 becomes negative b minus the square root of 0 over 2, again negative b over 2a. Therefore, x sub 1 equals x sub 2 equals negative b over 2a. Example. Solve 2x squared plus 4x plus 2 equals 0 by the algorithm above. Step 1. Compute delta. Delta equals b squared minus 4ac, which is 4 squared minus 4 times 2 equals 16 minus 16 equals 0. Because delta equals 0, the equation has one real double root. Step 2. Apply the case 2 formula. X sub 1 equals x sub 2 equals negative b over 2a, which is negative 4 over 2 times 2 equals negative 4 over 4 equals negative 1. To visualize the double root, look at the graph of y equals 2x squared plus 4x plus 2. The parabola just touches the x-axis at x equals negative 1 and turns around. That contact point without crossing illustrates a double root. Recap. We calculated delta, found it equal to 0, concluded a double root, and then used the simplified formula negative b over 2a to get x equals negative 1. That exactly matches the algorithm and the structure required for the delta equals 0 case. In this lesson, we will solve two quadratic equations step by step using the discriminate. We will follow the exact algorithm. First example coming up. Example. Our first equation is x squared minus 6x plus 9 equals 0. Step 1. Compute the discriminate. Delta equals b squared minus 4ac. Because delta equals 0, this quadratic has one repeated real root. Step 2. Use the special case formula x1 equals x2 equals negative b over 2a. Now substitute our numbers. Final answer for the first equation. Both roots are 3, a double root. Example. Our second equation is x squared plus 2x plus 1 equals 0. Step 1 again, compute the discriminate. Again, delta equals 0, so there is one repeated real root. Step 2, use x equals negative b over 2a and substitute. Final answer for the second equation. Both roots are negative 1, a double root. To build intuition, each equation can be factored as a perfect square. The first is left parenthesis x minus 3 right parenthesis squared equals 0. The second is left parenthesis x plus 1 right parenthesis squared equals 0. A perfect square parabola just touches the x-axis at its unique root. Recap. Step 1. Compute the discriminate equals b squared minus 4ac. If it equals 0, step 2, use x equals negative b over 2a to get the single repeated root. 4x squared minus 6x plus 9. The root is 3. 4x squared plus 2x plus 1. The root is negative 1. Great work! In this lesson, We will solve the quadratic equation 25x squared minus 30x plus 9 equals 0 using the quadratic formula, exactly following the classical step-by-step layout. Then we will visualize why the discriminant being 0 means there is a double root. First, identify the coefficients a, b, and c. Here, at equals 25, b equals negative 30, and c equals 9. We'll box each value right under the equation. Step 1, write the discriminant. Delta equals b squared minus 4ac. Now substitute b equals negative 30, I equals 25, and c equals 9. Then simplify carefully. When delta equals 0, the quadratic has a repeated root, also called a double root. That means both x1 and x2 are the same value. Write the quadratic formula. Then set delta to 0, to simplify, to negative b, to simplify, to negative b over 2a. Finally, compute the number. To see this visually, look at the graph of the parabola y equals 25x squared minus 30x plus 9. I will draw axes and the curve. Notice how the curve just touches the x-axis at x equals 3/5 and turns around. That single touch matches delta equals 0 and a double root. Summary: we computed delta equals 0, concluded there is a double root, and evaluated negative b over 2a to get 3/5. Therefore, x equals 3/5 is the unique solution, counted twice. In this example, we solve a rational equation by clearing the denominator, then reduce it to a quadratic and finish with the quadratic formula. Let's begin with the problem. Step 1. Clear the denominator by multiplying both sides by the factor x minus 3. We must note the domain restriction, x not equal to 3. After multiplying both sides by x minus 3, we get x times x minus 3 plus 1 equals 5 times x minus 3. Step 2. Expand and collect like terms. Expanding gives x squared minus 3x plus 1 equals 5x minus 15. Move everything to the left-hand side to get a standard quadratic x squared minus 8x plus 16 equals 0. To build intuition, here is the parabola y equals x squared minus 8x plus 16. Notice it is a perfect square, with its vertex touching the x-axis at x equals 4. Step 3. Compute the discriminant. Delta equals b squared minus 4ac. With it equals 1, b equals negative 8, and c equals 16. Delta equals 64 minus 64 equals 0, so there is one repeated real root. Step 4. Use the quadratic formula. X equals negative b plus, or minus the square root of delta all over 2a. Since delta is 0, both roots coincide at x equals 4. Check the domain restriction, x not equal to 3. Our solution x equals 4 is valid. Final answer x equals 4. In this lesson, we will solve a rational equation step by step, matching the structure shown on the screen. Here is the example we will solve. We will keep the work organized and move carefully through each algebra step. Step 1. Place everything over a common denominator. The common denominator is the product quantity x minus 7 times quantity x minus 5. Since a fraction equals 0 only when the numerator is 0 and the denominator is not 0, we can set the numerator equal to 0. Step 3. Expand each product. We use the patterns quantity x minus 5 squared and quantity x minus 7 squared, and expand the cross term as well. Now combine like terms. Then factor out a common 4 to simplify. Finally, divide both sides by 4. Step 5. Compute the discriminant. Here, a equals 1, b equals negative 12, and c equals 36. The discriminant is 0, which means a repeated real root. Step and c equals 36. The discriminant is 0, which means a repeated real root. Step 6. Use the quadratic formula. Since the discriminant is 0, both roots coincide at 6. Finally, check the domain restriction from our original denominators. We require x is not equal to 5 and x is not equal to 7. Since 6 is allowed, the solution is valid. Example: we will solve for a, and be given that the quadratic open parenthesis, a plus b close parenthesis x squared plus x plus 1 equals 0 has a double root at x equals 1. We will follow the textbook algorithm exactly. Use the double root formula. Derive the first linear relation, verify the root by substitution for the second relation, and then solve the two linear equations. Step 1. Use the double root condition. For a quadratic ax squared plus bx plus c equals 0, a double root occurs at x equals negative b over 2a. Here, a equals a plus b, and b equals a. Because the double root is at x equals 1, we set 1 equals negative a over 2 times a plus b. Now clear denominators. 2 times a plus b equals negative a. Rearranging, 2a plus 2b equals negative a, so 3a plus 2b equals 0. This is our first equation. Step 2. Verify x equals 1 is a root by substitution into the same quadratic. Substitute x equals 1. Open parenthesis, a plus b close parenthesis times 1 squared plus a times 1 plus 1 equals 0. Simplify to a plus b plus a plus 1 equals 0. So 2a plus b equals negative 1. This is our second equation. Step 3. Solve the two linear equations simultaneously. Write the system. 3a plus 2b equals 0 and 2a plus b equals negative 1. Multiply the second equation by negative 2 to get minus 4a minus 2b equals 2. Add the equations to eliminate b. Negative a equals 2, hence it equals negative 2. Substitute back into 2 a plus b equals negative 1 to get b equals 3. Also compute a plus b equals 1. Step 4. Visual check. With a equals negative 2 and b equals 3, the coefficient of plus b equals 1, and the quadratic becomes y equals x squared minus 2x plus 1, which factors as open parenthesis x minus 1 close parenthesis squared. The graph touches the x-axis at x equals 1, confirming a double root. Summary. We used the double root formula to obtain 3a plus 2b equals 0. Substituting x equals 1 into the quadratic gave the second relation to a plus b equals negative 1. Solving the system yielded a equals negative 2 and b equals 3, and the sum of plus b equals 1. The graph of y equals open parenthesis x minus 1 close parenthesis squared confirms the double root at x equals 1. In this example, we solve for a and b so that the quadratic ax squared plus bx plus 1 equals 0 has a double root at x equals 1. We'll write the problem and then build intuition with a quick diagram. A double root means the parabola just touches the x-axis and turns around at that x value. Let's sketch a parabola that kisses the axis at x equals 1. To have a double root, the discriminant must be 0. Delta equals b squared minus 4ac equals 0. Since c equals 1 here, that becomes b squared minus 4 equals 0. Also for a double root, the two equal solutions come from the vertex x value. X equals negative b over 2a. Our double root is at 1, so 1 equals negative b over 2a. Solve to get b equals negative 2a. Now combine both conditions as a simple system. Using b equals negative 2 inside b squared minus 4 equals 0, we get open parenthesis negative 2 a close parenthesis squared minus 4 equals 0. That simplifies to 4a squared minus 4 equals 0. Factor to 4 a times a minus 1 equals 0. A cannot be 0 or it would not be quadratic. So a equals 1 and then b equals negative 2. Therefore the unique valid pair is a equals 1 and b equals negative 2. These satisfy both the discriminant condition and the vertex condition, and geometrically the parabola y equals a times x minus 1 squared touches the x-axis at x equals 1. As a quick check, with a equals 1 and b equals negative 2, the quadratic becomes x squared minus 2x plus 1, which is x minus 1 quantity squared, confirming the double root at x equals 1. Example. We will determine the constants a and b from the domain information of a rational function. Here is the function. We are told that its domain is all real numbers except x equals 2. Our job is to use this domain fact to solve for a and b. Step 1. The domain of a rational function excludes values that make the denominator 0. Therefore, x equals 2 must make the denominator 0. Because only the number 2 is excluded, and the denominator is a quadratic, 2 must be a double root. That means the denominator equals the square of x minus 2. Now we equate coefficients with x squared plus ax plus b. Matching the x term and the constant term gives a equals -4, and b equals 4. To visualize a double root at x equals 2, here is the parabola y equals the denominator when it equals -4, and b equals 4. Notice it just touches the x-axis at x equals 2 and axis at x equals 2 and turns around. Therefore, the constants are at equals -4 and b equals 4. That single excluded domain value forced a double root at x equals 2. In this example, we will find all possible double roots given a relationship between the roots of a quadratic equation. Here is the given relation among the two roots x1 and x2. We are told the quadratic has a repeated root, which means the two roots are equal. If x1 equals x2, substitute x2 with x1 in the relation. That gives x1 squared plus 2x1 equals 3. Move all terms to one side to get a standard quadratic. In x1 squared plus 2x1 minus 3 equals 0. Now, factor the quadratic. It factors as x1 plus 3 times x1 minus 1 equals 0. Set each factor equal to 0 to solve for x1. So x1 equals -3, or x1 equals 1. Because the root is repeated, x1 equals x2. Therefore, the double root can be 1, or it can be -3. A quick check. If both roots are 1, then 1 times 1 plus 1 plus 1 equals 3. Works. If both roots are -3, then -3 times -3 is 9, plus -3 plus -3 is 3. Works as well. Summary. Using the repeated root condition x1 equals x2, we reduced the relation to a simple quadratic in one variable, factored it, and found two possible double roots. The equation can have a double root at 1 or a double root at -3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.